Hi, good evening. Can you hear me? Please confirm that you can hear me. Yes, sir. Okay. Mhm. I will share something. Share screen. Yeah. So that you can see my screen. Okay. Good evening. I'm Shoptal Sridhar. I'm a PhD scholar at IIT Bombay, Department of Electrical Engineering. I work on machine design for my PhD. This is a class of the doubt clearing class for the NPTEL course of Fundamentals of Electrical Engineering, which is taken by Professor Devapriya Das from IIT Kharagpur, and we take 3 doubt clearing classes every week, of which I take this Monday class, um, Monday 7 to 8, no sorry, not 7 to 8, Monday 6 to 8 p.m. Now, this week, this is the ninth session, uh, which is about single and three-phase AC circuit. In the uh, last session, we have discussed to some extent the the single-phase AC circuit. This week we'll discuss to some extent about single-phase AC circuit, and then we'll go to three-phase circuits. Before I go any more, just confirm once again that you can hear me. I am using a separate device today. What is this typing? Yes, okay. All right. So today we will discuss a very important thing before going into uh, solving the problems. Is that how to draw three-phase waveforms? Okay. You see, all the turbine-based or all the generator-based electric power generation are three-phase. That is because it gives the optimum value of power transfer by copper ratio, okay, and other advantages of three-phase motors, and all the three-phase motor came after three-phase power system came, and the instantaneous power of a three-phase system is, what to say, mm, is constant. It's not like a single-phase power which has ripple. Instantaneous power itself for a three-phase system is constant. Now, how three-phase power is generated? Say you have a turbine. This is the rotor of the generator, and you have poles. So two-pole system. So north and south, like this. Now, what you have is, say you have one winding here, one phase here. So this is, let me, say one winding is here, cross and dot, one phase. Now, if this is one phase and you have three phases, so we will put them in 120-degree fashion, 120-degree phase shifted. So let me draw a bigger diagram that will be easier. So if one phase is pointed towards this direction, that is, say, the cross of one phase is in this direction, the other one will be lagging by 120 degree. That is, the other one will be here, and the third one will be here. Okay? Like this. And the corresponding dots will be at the opposite direction. That is why, sorry, that is why the energy, that is power, that is generated, or the voltage that is generated, better to say, not power, voltage is generated is 180-degree phase shifted. Now, if we take a phase sequence of A, B, C like this, what we can say is VA. Let us talk about phase voltage. Okay, so VA with respect to some neutral N, phase voltage is some amplitude V sine omega t. Okay. Now, phase sequence is ABC, so B will lag A by 120 degree. So if B lags A by 120 degree, that means VBN will be V sine omega t minus 2 pi by 3, and VCN is lagging A, lagging B by even more, even 120 degree more, that is V sine omega t minus 4 pi by 3, which is also equal to, since it is cyclic, so minus 4 pi by 3 or minus 240 degree is also equal to plus 120 degree. It's like this. Now, it's very important that you can draw phase voltage and line voltages by yourself. Not only for your understanding, but also in later stages, you will study power electronics, something uh, called three-phase rectifier you will study. So, and other things also. So unless you can draw voltage waveforms, phase and line voltage waveforms by yourself, it is not possible to understand the working principle of these rectifiers and some other things also. Okay, so now we will see how to draw a three-phase voltages. Okay. Now, you should always do this thing on a graph paper. All right. So what you do is take a millimeter graph paper. A millimeter graph paper is like this. So you have these boxes which are 1 centimeter, say, wide. Okay. Now every box, so one box for 1 centimeter, you mark as 30 degree. So at the bottom of the grid that I have already made for today's class, at the bottom of the grid, you see once I have made the grid for 30 degree each. Okay. So if you want to draw, if you're going to draw three-phase voltage waveforms, current waveforms, you should make a grid of 30 degree. If you try to make larger, that will be problematic. You will not get all the angles that you need, and smaller you do not need. Okay, so this is enough to have 30 degree grid. Okay. Now we will start with drawing phase voltages. Right. So there are three. What I will do is I will draw phase A with red, phase B with green, and phase C with blue. Okay. Sometimes you will see some people say ABC, sometimes people say RYB. In some books, I think in some Russian publications, you will get to see UVW. It's the same thing, 120-degree phase shifted. Okay. Now, if this is the thing, now look at the equations that I have written on the right hand side. VAN, BN, and VCN. We will draw this phase voltages. Now you can see from VAN that at t equals 0, VAN has the positive zero crossing. What is a positive zero crossing? Positive zero crossing is when a, the curve crosses zero and becomes positive. That is positive zero crossing. And when a curve crosses zero and becomes negative, that is negative zero crossing. This is positive zero crossing and this is negative zero crossing. So from the phase voltage equations that we have written here, we can say that VAN has positive zero crossing at 0. Theta equals 0. Theta is omega t. Okay. Now, what we will do is we will quickly mark the zero crossings and the peak values of the waveforms. We will start with phase A. Okay. So phase A has a positive zero crossing. I am marking with red dots. I hope you can see. Has a positive zero crossing here. Yes, there is visible. Now it will reach the peak at 90 degree. We know that sine reaches peak at 90 degree. So 0 plus 90, 90. It will reach its peak here. And then it will go through its negative zero crossing at 180 here. Now it will reach its negative zero crossing again after another 90. So 180 plus 90, 270. It will reach its negative zero crossing. Then again 270 plus 90, 360. It will reach its positive zero crossing. Now we have got the dots to draw phase A voltage. We can draw phase A voltage like this. We can draw phase A voltage like this. Okay, phase A is done. Now we have to draw phase B, phase voltage B. Now you see phase B is lagging phase A by 90 degree. What does that mean? That sorry, not 90, by 120 degree. What does that mean? That means if phase A has a positive zero crossing somewhere, phase B will have the positive zero crossing after 120 degree. So it had a positive zero crossing at 0, phase A. So phase B will have a positive zero crossing at 120 degree here. Green dot is visible? Yes. Now, if it is crossing 0 here, so 120 plus 90, 210, it will reach its peak, positive peak. Again, 210 plus 90, 300, it will reach negative crossing, 0 crossing. Again, where is it? 300. So 300 plus 90, it will reach its negative peak. 300 plus 90 is 390, which is 30 degree. It will reach its negative zero crossing. Sorry, negative peak. Again, 30 plus 90, 120. It will reach positive zero crossing, which we have already marked. So now we have got the dots to draw phase B voltage. So we can draw phase B voltage. We can draw phase B voltage. If you draw these things in a graph paper, sorry, I made a mistake. It is coming to 0 here. If you draw these things in a graph paper, that looks even more symmetric, is phase B. Now, similarly, I have to draw phase C. So phase B had a positive zero crossing at 120. So phase C will have a positive zero crossing at 240, which is here. So 240 plus 90, 330, it will have its peak. 330 plus 90, 420, that is 60 degree. It will have negative zero crossing. And 60 plus 90, 150, it will have its negative peak. 150 plus 90, 240, positive. Now we can draw this. So this is how we draw the phase voltages of a three-phase system. Now, here you notice something very interesting. You look where the curves are crossing each other. Say where the red curve and the green curves are crossing, where the um, green and blue, red and blue, where are they crossing? See, I have marked every 30 degree from zero. You see all the crossings where the red and blue, say for example, you take the 30-degree mark, there the red and blue are crossing. All the crossings happen at some 30 degree, at some mark. 30 degree there is a crossing, 90 degree there is a crossing, right? Okay. You notice one more thing. Whenever there is a crossing mm, between two waveforms, say take the 30-degree crossing, where the red and blue are crossing each other. At that time, the other one is at its peak, either at positive or at negative. So basically, if the other one, say at minus 2 volt, say the green one is at minus 2 volt at 30 degree, then the red and the blue both are at plus 1 volt. So the summation is 0. So it's an observation. So at 30 degree, there is a crossing. Again, at 90 degree, you see red is at its peak, say 2 volt, and blue and green are both having minus 1 volt, minus 1 volt. Okay, just an observation. All right. Now we have phase voltage. Once we have phase voltage, okay, I will make some space here. Okay, once we have the phase voltage, now we can draw the line voltage. Now line voltage, if there is delta, okay, so let us say delta connected supply. So delta connected supply like this. So if we have a delta connected supply like this, then definitely phase voltage is same as line voltage, because line voltage is this. Line voltage is this, and this is also the phase voltage. So phase voltage is definitely the line voltage, but currents are not the same, because you can see that line current and phase current are not the same. So what happens is, magnitude wise, uh, line current RMS is √3 times phase current RMS. And if you look at star connected supply, let us say, in this case, phase voltage and line voltage, they are not same in magnitude, because this is the phase voltage, line voltage. Line voltage means line to line voltage, and this is the phase voltage. So they are not same. So RMS, if I write RMS V, sorry, line voltage RMS equals √3 times phase voltage RMS. Do you guys know the derivation? Why the line voltage RMS is √3 times phase voltage RMS? And for star, currents are the same. So even instantaneously we can write line current is equal to phase current. Okay. All right. So if we have VAN, VBN, VCN like this, what will be our line voltages VAB, VBC, and VCA? I need your feedback here. Do you know how to get phase voltages from line voltage by geometry? I mean, by phasor or by trigonometric calculations? Anything? No. Okay. So we'll go through phasor. Why I am stressing so much on three-phase system is it's very important concept. All high power machines, power electronics, all are based on three-phase, and it's very important that you have a very crystal clear idea about three-phase systems. You should be able to draw phasors and waveforms and everything. Okay. How many of you did say no? All right. Sujay was going to say something. He was typing in here. So we'll draw the phase voltages first. Phasors. Okay. Now phasors, if I draw, it's difficult to draw. Let's see. Say here is one phase voltage, say phase A, and this is one. Whether phase A or B, we don't know. This is another. Okay. They're 120 degrees shifted. Now, I have said that this one is phase A voltage VAN. Now, which one is phase B? Our convention says that phasors are rotating in anti-clockwise direction. So if I look from here, so what I see is phase A crosses, then this one crosses. So this has to be phase B, right? And this is phase C. So A phase voltage, B phase voltage, C phase voltage, we know. Now we are trying to find out line voltage VAB. So what is VAB? By definition, it is AN minus BN, VAN minus VBN. So to do that, okay, I have to do it by hand. So AN minus BN means AN plus minus BN. So I have to draw minus BN first. Minus BN will be here. I think I have to insert some space. Yeah. So minus Bn is here. Now I have to simply add up these two phases. So how to add up? This I draw. Okay, let me remove the I. There we go. this. And so definitely VAB will be lying here. Lying here. Now, what is the angle? We'll see first. See, we can simply say that, sorry, just by observation, we can say that this angle is 60 degree, right? This angle is 60 degree, and these two vectors which we are adding, they are equal in magnitude. So definitely their resultant will bisect the angle between them. So this angle is definitely 30 degree. This much we can say by observation. But magnitude we cannot, just by observation we can do. So magnitude wise, what is the resultant magnitude? Which is, we know that if there are two vectors A and B, if there are two vectors A and B, then let me not go here. Okay, I will write here. Then the magnitude of their resultant is A squared, obviously magnitude of A, B squared plus 2AB cos theta. So in this case, both of them have the same magnitude, VV, right? So V squared plus 2 times V times cos 120 degree. Their angle was cos 120 degree. Now, what is cos 120 degree? So shame that I forgot. It's minus half. Cos 120 is minus half. So what you have is 2V squared minus, wait, where am I making a mistake? Is it plus or minus? Let me do a quick Google search. No, it is plus. A squared plus B squared plus 2AB cos theta. Should be 3V. Why did it go wrong? My goodness. Cos 120 is minus half. Why am I getting V? Can you guys spot the mistake? Someone is writing in the chat. Yes, cos 120 is minus half. Cos 120 cannot be plus half. That is sines quadrant. Can you spot the mistake? Oh, I did A minus B. Sorry. This is A minus B, right? VAN minus VBN. I use the formula of addition. We are doing a subtraction here. See here. We are doing a subtraction here. So minus, minus, minus. So it becomes plus. So what we have is square root of 3v squared, which comes out to be root 3v. Okay. Uh, so basically what we can say from here is that our line voltages will be root 3 times the phase voltages, and they will lead them by 120. Now you have VAB, so like VB lags VA by 120 degrees. Okay, let me write. Do not get confused. Say if you have the phase sequence ABC, so if VAN, VBN, VCN is the sequence, all lagging each other by 120 degree, then VAB, VBC, VCA will be the sequence, all lagging each other by 120 degree. Okay, so if AB is there leading VAN by 30 degree, we should have VC here leading VBN by 30 degree. Can you appreciate that they are leading? When I say leading, do you appreciate from the phasor? So similarly, VCA will lead VCN by 30 degree. So this is this is 30. This angle is 30. This is VBC. This is VCA. Okay. Now we can, from the equations above, phase voltage equations, we can quickly write the line voltage equations. Where does the blue see that? So we can write VAB is root 3 V sine omega t plus 30 degree, which is 5 by 6. You can also write in degrees. Okay, not a problem. If that is easier to write, you can write in degrees also. VBC, but if you're writing in degrees, do not forget to mark the degree. If you write in degree but do not show the degree, it will by default be treated as radian because omega t is in radian. VBC is root 3V. Now, we need not look at them. We simply lag it by 180 degree. Sorry, 120 degree. So it becomes minus 90 degree. And VCA will lead AB by 120 degree. So it will become this. Now, why I did all this is that once you have V phase voltage, you have drawn the phase voltage, you should also be able to draw line voltage. Okay, because in rectifiers you will see both the voltages will be required in order to understand how the output voltage waveform will look like. Maybe in your third year or so you will study, or I don't know, maybe some of you already studied it. So first we'll draw VAB. Now this was our V, the red one. I should have marked. Red one was our VA. And we have seen that VAB will lead VA by 30 degree. So lead VA means, so VA had its peak at 90 degree. So VAB will have its peak 30 degree earlier, so 60 degree. So VAB will have its peak here. So if its peak is here, now we can find out the other things. Simply keep on adding 90. So 60 plus 90, 150, plus 92, 40, plus 93, 30, plus 94, 20, which is 360 this. So I'll quickly draw. I don't know why is it so thick. Sorry. Does it?
Sir, you are not audible. You are on mute, sir.
How long am I mute? I didn't see. I don't know how it got mute. I didn't mute myself. Okay, anyway, thanks. How long did I say? How long could you hear? Do you hear this? Where we got root 3v? No answer. Am I still mute?
No, no, no.
Could you listen to this up to this derivation of root 3v? Someone else can also say.
Yes, sir, yes. This
Okay.
was audible.
So what I said is VA we know, and we know that VAB leads VA by 30. So at our phase voltage curve, VA had its peak at 90 degree. So VAB will have its peak at 30 degree before 60 degree. That way we could draw VAB. Now we know that VBC will lag VAB by 120. So we could draw VABC, and VCA will lag it even further, or we can say it will lead VC here by 30 degrees, same thing. Now we can quickly draw VCA. Its peak is here at 300, so 390 30° will cross -0, 120, 210, and 300. So the waveform looks like this. हाँ ठीक है ठीक ये स्लाइड चेंज नहीं होता है इसका खराब हो गया पता नहीं
ठीक है दिखाने के लिए तो
हाँ पॉइंटर चलता है डाउन हो गया
ठीक है मैं ले लूंगा
ठीक है
चार्जर वाला है
नहीं और then it will go like this. Why are these lines so heavy? I don't know. I did not change anything. Red one also the same. Anyway, so like this you will get. So this is how you draw three-phase voltage and current voltage. And now if you have current, say, you know that the load current is lagging line voltage by some angle, you can again draw it on this curve by lagging and leading. Okay, so it's very important that you know how to draw the voltage and current waveforms of three-phase systems and the phasor also. Phasor is also very important. Say, for example, we have this. Now we have a load which is 30° lagging. Oh, here one more important thing. So suppose we say that there is a three-phase system which is rated as 400 volt, 50 hertz. What is this 400 volt? Which voltage is this? Is this phase voltage or line voltage? Someone quickly unmute and tell. So whenever we are talking about three-phase system and simply say it's a 400 volt system and don't say anything else, it means it is line voltage. It is line voltage, and as usual, it is always RMS. That is the convention for AC system. It is always RMS, but when it's three-phase system, always remember that it is line voltage when you are not mentioning it otherwise. Now, very easy way to, I mean, in case sometime, let me remove this. In case sometime you get confused, so remember that the neutral wire is not always available to you. So these three are the lines, and the fourth one is, let us say, the neutral wire. Now, if you put a voltmeter between this and this, then you will get a phase voltage. But this neutral wire may not always be available to you, but the lines are always available. So it's easier to measure line voltage. We always get line voltage. That's why it's customary to rate the three-phase systems in terms of line voltage. Okay. All right. Okay, so now it's time to take your doubts. So if you have any doubt in this discussion or the lectures of this week or maybe previous weeks also, anything you have to ask. I'll just check once more if I mute. No. So you have something to ask? Anything to ask? No doubts? Okay. All right. We'll start with the questions. It's taking some time to synchronize. Wait for 5 minutes. Okay, we'll start with that. Not 5 minutes, 4 minutes maybe. What happened? Today is week 9. Week 9. Week 9, I have. Okay, let's start. Please make it a habit that whenever you are solving problems of AC circuits, to draw a waveform, to draw a phasor diagram. Okay? Even if it is not asked in the questions, even if you are not asked to draw a phasor diagram, make it a habit to draw a phasor diagram for your understanding. And in these two questions, synchronizing. Anyway, we'll start. A single phase series RL load. It's a single phase question. Okay. Single phase series RL load operating at 230 volt 60 Hz draws 2.8 ampere current at power factor of 0.8120 lagging. Okay, so RL load 230 volt 60 Hz 2.8 ampere current it draws at power factor of 0.8120 lagging. If the same load is connected to 415 volt 50 Hz system, find the real power consumed by the load. So basically, the data that we have been provided with, that should be able to give us the load information, the whole load parameter which we should be able to get, R and L. Okay. Yeah. Now, it draws 2.8 ampere current at 230 volt. So what we have is V RMS by IRMS. Nothing is mentioned, so this is definitely RMS. So VRMS by IRMS is 230 by 2.8, which gives us 82.14. So 82.14 ohm. This is the impedance. Magnitude of the impedance is 82.14 ohm. Now, what else do we have? We have the power factor. So omega L by R there is an angle. So wait, tan inverse omega L by R gives us the power factor angle. Cos of that gives us the power factor, that is 0.8120. Okay. So what we have is tan inverse omega L by R is cos inverse 0.8120. So that comes out to be 35.71 degree. Tan of that is like this. And from here, what we have is this one is equal to square root of R squared plus omega L squared, or in other words, R squared plus omega L squared is 82.14 squared, which is 6746. These are easy things, they are only calculations, no engineering involved. Right? Now you can write omega L in terms of R from this equation. So it's R squared plus 0.7188 times R squared equals the 6746.98. Then what we have is 6746.98 divided by 1 plus 0.7188 squared, that is R squared. Now square root of that gives us the R. So what we get is R comes out to be 66.7 ohm. Now if R is that much, then what is omega L? Omega L is this times 0.7188, which is 47.94 ohm. Now it's 60 hertz, so omega is 120 pi, right? 2 pi f, 120 pi. So if I divide that by 120 pi, what I get is 0.127 Henry. This is what we get. Now this load, this RL load is fed, this RL load is fed to a, I'm not sorry, but this RL is being fed by 415 volt 50 hertz, 415 volt 50 hertz system. So now definitely omega L is not changed. So our new Z at, sorry, our new Z at 60 hertz, so 50 hertz will be R is same 66.7 squared plus omega is now 100 pi times 0.127, which gives us 77.7. Definitely the frequency reduces, so the impedance reduces. It's an RL circuit. This is the new impedance. So what will be the new RMS current? New RMS current will be 450, or this load will draw an RMS current of this by Z, which gives 5.34 ampere. Now this RMS current is flowing through the resistance and causing some power loss. That power loss we have been asked to find out. So it's simply I squared times R. So this gives us 1901 watt. This is around 1.9 kilo. Okay. Some error is there. Just a minute, I think. Did not sync here. There are some error in syncing. Okay. Any doubt in this? Easy question. Just find out the values of R and L. It's only about calculations. Okay. We'll look into this question now. The question says, okay, a single phase 50 hertz to 30 volt RMS, even if they do not mention RMS, it is RMS, you know, is supplying three loads in parallel. Oh, this one is interesting question. Parallel, 2.4 kVA at leading power factor of 0.8, 4.88 kilowatt at lagging power factor of 0.9, 900 watt at unity power factor. So there is one source. There is one source which is supplying three loads, okay, in parallel. So three loads are there in parallel like this. There are three loads in parallel. Now, there is a the question is, a capacitor is connected in parallel across the combination of the three loads so that the current supplied by the source is in phase with the source voltage. Find the value of the capacitor. Now, before we solve this problem, we'll have a general discussion. Say, we have an AC source like this, an AC source, and it is supplying an RL load. RL load is a lagging load, right? So what you have is, if this is the source voltage, say Vs, and this is the load current IL, then definitely it will lag. The phasor is like this. Now, so this IL, so if I now draw IS, source current, as of now what we have is IS equals IL. So the uh, the AC source is seeing a lagging current, but I do not want the I do not want a lagging current from the AC source. I want unity power factor current from the AC source. Why? We will see after we complete this discussion. But suppose for some reason I do not want a lagging current or leading current. I want pure perfectly unity power factor current. So what we have to do is, if we look at IL has two components. If I draw IL, the components of IL, it has two components. But yeah, so if I find the components of IL, one is along this, which is lagging Vs by 90 degree. Another one is along Vs, right? I'll draw it here. Another one is along Vs. Now we know that the current that is along the voltage source, that is the one that contributes to the power. The other one is only the reactive power, right? Now this current is the one that we do not need or we want to get rid of. Then we will get a unity power factor. So what we do is we connect a capacitor in parallel. Once we connect the capacitors in parallel, the capacitors start drawing a current IC. Now IS is now no longer equal to IL. IS is equal to IL plus IC. Now why will IC be IC? IC is a capacitive current, so it will lead Vs by 90 degree. So it will be somewhere here. It will be somewhere here. And its magnitude would depend on the value of the capacitor, right? Now, we choose the value of the capacitor such that these two lengths are equal. These two lengths are equal. Then what is happening? Then if you do the vector addition of the currents IL and IC, what you get is IL. Wait, IL was this red vector, sorry. IL was this red vector plus IC. So at the end, what you get is the blue vector. This one. Now this blue one is now the source current. So the red one is the load current. Green one is the capacitor current, IC. And IS is the source current. Now try to understand what we gained from this. Okay. First of all, our priority is the load. The load must not be affected. You see, the load has not been affected because the voltage across it is still the same. The capacitor was connected in parallel. So it did not see any difference. Whatever current it was drawing previously, IL, that much current it is drawing. What we did is we added a leading current such that the source current is now IS instead of IL. Now this is the thing where I will tell you why we would need a unity power factor. The reason being, you look at this triangle. this IS, IL, IC triangle. I will draw them separately here once again. Look at this triangle. It's a right angle triangle, right? Right angle triangle. And IL is the hypotenuse, IS is this, IC is this. So definitely IL is greater than IS, right? In magnitude. In magnitude. That is greater than IL. So basically what happens as soon as the capacitor is connected in parallel, the current drawn from the source reduces. Now remember, the power drawn from the source is the same because capacitor does not draw any power. So the power drawn from the source is still the same, but the same power is being delivered at much lesser amount of current. Now you see all the losses in the transmission line, in the generator and everything, all the ohmic losses, that is I squared R, simply I squared R. And here we do not care, means it doesn't matter whether this current is leading or lagging or unity power factor, doesn't matter. Loss is I squared R. So definitely at the very beginning, means when we did not have the capacitor, we were supplying some power where we were encountering much higher resistive loss. After putting the capacitor, our power factor improved. So what happened? We are now supplying the same power, but at lesser current. Hence, the power loss encountered by the system is reduced. So this is why we want unity power factor, and this thing is called power factor correction. Okay. At your home also, the power that you draw is not unity power factor because you have fans and other motors running. But the power factor at your home is not very bad. It's more than 0.9. It's not very bad. But big industries, they are running large induction motors and other loads. Their power factor is very bad. That's why the companies, the power distribution companies, say for example, in Maharashtra we have the Mahadiscom, Maharashtra distribution system something. In Bengal, it is WBSC DCL Distribution Company Corporation Distribution Company Limited. Anyway, so they charge the industries for reactive power also. Those distribution companies would charge you as a domestic user only for the active power because your reactive power is very less. The distribution companies would install small capacitors in the transmission lines to take care of your reactive power. But industries draw a large amount of reactive power, and that is problematic for them because to supply the same power, the current is much more. So the transformers become oversized, transmission line become oversized. So to stop that, they would charge the industries for reactive power also. Okay. And what the industries do, in order to get rid of this charge, they generate reactive power locally. How do they generate? One way is to have a capacitor. So the transmission, say the generator is somewhere far away, say 100 kilometers away. This is the transmission line, and here is the industry. It is the load of the industry, which is heavily reactive. What they would do in their premises, they will connect another capacitor. So whatever lagging power, whatever reactive power they need for their motors to run, that will be supplied by the capacitor. And since the reactive power is being delivered locally, this transmission line is relieved. of the reactive power. That doesn't have to supply the reactive power. Okay. Now capacitors, as I said, now there are several problems capacitor, because as you can see that it depends on the load, how much reactive power you need. On that, it would depend how large capacitor you need. Now, if your reactive power keeps changing, you have to keep changing the capacitor. You cannot keep doing that. So you need a controlled capacitor that will be controlled in a closed loop fashion. So that is done by some converter. We'll study later maybe, which is called STATCOM. Static compensator. Compensator, what does it compensate for? It compensates for the reactive power. Also, there is one more thing which used to be very popular, I think now also. Some industries use, which is synchronous condenser. You know that capacitors are sometimes called as condensers by people. Now, synchronous condenser, we will study these things later, is a overexcited synchronous motor. It's a regular motor, but its field excitation is made more than rated, overexcited. So this motor, along with its regular job, also puts reactive power in the system so that you can generate your reactive power locally. Okay, so that's a discussion about reactive power. I believe the way of drawing phasors and all you remember. Very interesting thing. I find it very interesting. Anyway. Okay, any doubt in this discussion? Power factor correction and all? Okay, we'll look into this question. So we have read the question already once. A single phase 50 hertz, this thing is supplying 3 loads and the capacitor is connected in parallel so that the current supplied by the source is in phase with the source voltage. Find the value of the capacitor. So what we have to do is we have to find out the current and then find out how much reactive power, total reactive power the load is drawing. So one of them is unity power factor. We need not consider that in our calculation. The last one. We need not consider that in our calculation. We have to consider about the other two only, 2.4 kVA and 4.88 kilowatt. Now, do you know what is kVA? kVA is apparent power. So when they say it's 2.4 kVA, so we'll write load A, load I. It's 2.4 kVA, so the current that it is drawing is simply 2.4 K by 230 kilovolt by volt ampere by volt. That gives us ampere. This much current it is drawing. So it becomes 2.4 K by 230, 10.43 ampere. That is the RMS, but it draws the current at a leading power factor of 0.8. Right? So if I write the I1 in vector, it becomes 10.43 angle cos 0.8. I am taking the voltage as reference. So, sorry, not cos inverse. Cos inverse 0.8 is somewhere close to 36.86. its angle. So this much current it is drawing the first load. Now we will look at the second load. Okay. The second one is 4.88 kilowatt. The other one was kilovolt ampere. This is kilowatt at lagging power factor of 0.9. So here the current is 4.88 kilowatt by voltage 230 times the power factor, because we know, right, IRMS times VRMS times the power factor gives us the power, the real power. So real power divided by voltage times power factor will give us the current, RMS current. So how much is the RMS current? 4.88 10 cube by 230 times 0.9. RMS current comes out 23.57 ampere, and if I write it as a vector, it's 23.57 angle minus it's lagging cos 0, so cos inverse 0.9, 25.84 minus 25.84 ampere. Now this much is enough for our calculation, but still for the sake of completion we will calculate the current for the load 3 also, that is not required. Okay. Because we have to just find out the reactive power. For the sake of calculation we will do, completion we will do. I was telling before you joined that whenever you are solving problems for AC circuits, make it a habit of drawing phasors, even if it is not asked. I solved single phase problems, but this lecture is for everyone, and this being recorded also. This will go to YouTube, so others who cannot come to the class, they will also refer to this lecture. So I have to do. So you said you can solve. Okay, I hope you can help me solving the rest of this. Okay, so what is the current of the third load? Quickly, what will be the current of the third load? Do you have a calculator at your hand? What is the current of the third load? Sorry if you see the question. .91 angle. Angle 0 degree. Now, okay, what is the next step? Can you please unmute and talk? That will be faster. This is a single phase parallel circuit. So while drawing the phasors, which phasor should I take as the reference phasor? You got my question? This is a single phase parallel circuit. So while drawing the phasor, which phasor should I take as the reference phasor? Sir, I3? Why I3? Why not I1 or I2? Equivalent, right? They're in parallel. So why suddenly I3? It is at 0 degrees. So suppose in this question they had said this 900 watt not at unity power factor, at some other power factor, the point line leading. In that case, what would you take? Anyone can be taken, Nasser? No, anyone cannot be taken. Your whole life will pass to complete the phasor diagram drawing. So whenever we are drawing, I will remove this. So whenever we are drawing phasor diagram for parallel circuits, our reference phasor will be the voltage of that parallel branch, because voltage is same for all of them. On the voltage, we will draw the currents. Okay, so I will draw the voltage with red maybe. So this is my voltage, supply voltage Vs. Now we will draw the first current. First current I will draw with green. First current is leading. First current is leading. So it is somewhere here. And it's leading by quite a large angle. It's small angle is somewhere like this. This is I1. This is V, supply voltage V. The second one is lagging and it's higher in magnitude. Second one is lagging, lesser angle but larger magnitude, somewhere here maybe. I2. And the third one will go with black. That is in phase with supply voltage. Oh, it's very less in magnitude. Very less in magnitude. So somewhere here. Now what we can do is, although it is not required, but as I said, that make it a practice to draw phasor diagrams. No, not like this. This is not wrong. Anyway, so I1, this is, as I said, it is I3. Now you can add them up. So this is I1 plus I3. With that, you add I2. Sorry. This is I2. I hope it is okay. Let me. Anyway, it doesn't matter. Just aha. Oh, I'm wasting some time here. I2. Now the resultant that we have is this. Resultant is this. This is the source current, let us say, I guess. Now you can see that the source current is lagging. Actually, drawing can be wrong. We will find out whether it is really lagging or not. How to find out? We will find out if I write like this, I and J, we will find out the J-axis component of all the currents. It means I1 and I2 currents. So this one was 36.86 degree. So if I find out the J-axis of the total, what it becomes is, I'm doing, you tell me if you don't understand. 10.43 sine, the reactive component basically, 36.86 degree, that is upwards, and for the other one it's downwards, so minus 23.57 sine 25.84 degree. So what you get is 10.43 sine 36.86 minus 23.57 times sine 25.84, which gives you a negative value, minus 4.01. Minus 4.01. So I took this one as positive. I took, see, the first one, 10.43 sine, I took as positive. So, and we got negative. So basically this much is the reactive power component of the resultant current. So I have to connect a capacitor here. I have to connect a capacitor here that would draw a current of equal magnitude. That is a capacitor that would draw 4.01 ampere of current, or angle 90 degree ampere of current from 230 volts. So XC comes out to be 230 by 4.01, which is 230 by 4.01, 57.36 ohm, which is 1 by omega C. This gives us a C of omega is 100 pi, 50 hertz. Yes, 50 hertz, 100 pi. This answer inverse into 10 to the power 6, if I do, some 55 microfarad I would need. Tell me, any doubt? Yes, frequency is 50 hertz. So omega is 100 pi. Okay. Okay, you type if you have, okay, since you said about three phase, we'll do some three phase. These are actually easy questions. We have done things like this. Okay, some 2-3 questions on three phase we will do them. A three-phase, three-wire system has a balanced delta-connected load. Okay, balanced delta-connected load. Whenever there is a balanced load, what do you mean by balanced load? It's AC. Okay, so balanced load. So an AC load is a impedance Z, which is a vector, which is written by its magnitude and angle. Three-phase balanced load means all the loads, all the three loads have the same amplitude of impedance and the same power factor angle. Okay, power factor angle sign is also considered. Like if one of them is 30 angle say minus 25 degree, all of them should be 30 angle minus 25 degree only, considering the angle. 30 angle 25 will not be. That means they cannot come with them. Make a balanced load. Okay. Now three-phase three-wire system balanced delta connected load. Whenever you are doing, especially as a first year students, I don't know where you are studying, make it a habit to draw phasor diagrams whenever you are solving AC circuits, especially three-phase AC circuits. So balanced load of delta connected has 18 ohm resistance, 100 milliohm Henry inductance, 100 microfarad capacitors in series at each phase. Assuming ABC phase sequence in power. Okay, so what we can do first is the find out the Z magnitude. So Z magnitude will be 18 squared plus, I'll quickly find out. So 100 millihenry in 50 hertz, that will give us 100 10 to the minus 3 into omega A. So 100 pi, 10 pi, 31.42 ohm, and 100 microfarad at 50 hertz gives us 1 by omega c. So 100 pi times 100 10 to the power minus 6, 31.83. 31.83. So they almost resonated. Almost resonated. So it's 31.42, but you can see it's a capacitive load. It has become a capacitive load, slightly capacitive load. Okay, it will come very close to 18. Okay, I'm not doing this calculation anymore. Somewhere close to 18 only it will come. So 18 ohm resistance you have, or impedance you have in all the branches. And question is total power taken by the load. So what we will do is we will find out power in one phase, multiply with 3. Now this is three-phase three-wire system, 230 volt. Again, they have mentioned line-to-line voltage, but even if they do not mention, or if nothing is mentioned, it is line-to-line voltage only for three-phase. So this is 230 volt. You can see that line voltage is nothing but phase voltage, as the load is delta connected. Just from the circuit you see. From the circuit itself, you can say that the line voltage is nothing but the phase voltage, right? So phase current is phase voltage by resistance or impedance is 230 by 18. Around 12.78. 12.78 ampere. So what is the power? Power is 3 times per phase power. Which gives some 8.81 kilowatt. We will quickly draw phasor diagrams, although it is not asked, but I said that make it a habit. So what we can write is, this is, I am drawing the phase voltages. Okay, so phase voltage, which is also the line voltage. So you can write, say, VAN is also equal to VAB. Similarly, VBN, which is VBC, okay, let me write, and VCN, which is VCA, AB, BC, CA. Okay. Now, I said that the line phase current is a bit leading. I will intentionally draw it leading to give you an idea how to draw. So, phase current is this. This is the A phase current, which is leading phase A by a small angle. Phase B current and phase C current. Right, something like this. Now, suppose, now this is very important. So you have 3 phases A, B, and C. So how do you mark the phase line currents? IA, IB, IC. Now, there is a line current, phase current. How will you mark? So this is from A to B. So IAB, B to C, IBC, C to A, ICA. Now, if you apply KCL at this node, what we will get is, our problem is done anyway, okay? So what we will get is, we will get IA plus ICA is equal to IAB. In other words, IAB minus ICA is IA. So what we have drawn in this phase, there are phase currents. This is IAB, IBC, ICA. Now to find out line current, what we have to do is we have to subtract ICA from IAB. Subtract ICA from IAB. So let us draw ICA. Okay. Wait. We'll make it thin. So ICA is somewhere here. So now I will add them. Wait, am I doing some mistake here? Should come on the other side. Am I Sliding IAB, ABC, ICA. Wait a minute, I think I made a mistake. Just a second. I'm expecting it on the other side. Why is it coming at this side? I line should lead, right? Tell me if you can find out. This only we did some time back, right? Let me check with other currents. Is the same mistake am I doing? I see those. AC plus ABC, ABC. So I see a minus ABC if I do. Why am I getting why did I make a mistake? My conventions are correct. If this is A, B, C, then A, B. Write in chat if you find out. So we'll see. We'll look at the next question. I'll find out. It should not be that difficult. Did I write the KCL correctly? IA plus ICA. Is IAB. The KCL is correct. Okay, let us draw all three. Just see who leads on. Okay. So if we draw, say IC minus IAB, one current comes here. If IAB is 0, this should be 30 degree. You think sequence? Sequence is correct. So one will come here. And ICA minus IBC. So will come here. Will come here. This KCL is wrong. It is where the KCL wrong. Wait a second. Like this. No. Okay, anyway, we'll see. Maybe I will find out and tell you in the next class, okay? We will quickly solve one more problem. So this is why it's important that you keep these things in practice. Anyway, to solve this, look into it. Balanced three-phase three-wire system is a line voltage of 440 volt. Two balanced three-phase loads are present. Okay. One is star connected capacitive load. Other one is a delta connected inductive load. Observe that the three-phase system altogether supplies P kilowatt power at PF power factor. Find the correct choice for P and Q. Okay. So star connected capacitive load is, I'm not drawing the capacitor and resistors. This and delta connected inductive load so if I mark this terminals as ABC and BC, then this is one. Here. No. B and C. Okay. All right. So star current capacitive load. Okay, so to find the power factor. So when you are simply asked about the power factor, that means if you have to look into the line current and the line voltage, and their relation will give you the power factor. Okay, so basically what you have to find out is this current and this current, then find their vector summation. So I will call this current as say IS star current, call this as ID delta current. Now for the star connected system, let us write them in time domain. Okay, it's a 440 volt. So let me write voltage AB, line voltage is 440 root 2 sine theta. Theta is omega t. Right? Now, if that is the line voltage, then phase voltage will lag line voltage by 30 degree. Phase voltage will lag line voltage by 30 degree. So it will be 440 root 2 by root 3, 359 sine theta minus 30 degree VAN. Now, once you know VAN, we can find IS. IS, right? So this load 24 angle, so 24 minus J, I'll write it here. 24 minus J 18 can be written as square root of 24 squared plus 18 squared, which is 30 angle what I'm doing is tan inverse 18 by 24, 36.87. Degree. This is the capacitive load. Now this will cause a leading current. So what we have is 359 by 30 sine theta minus 30 plus Okay. Can you please confirm that you can hear me? Quickly. Can you hear me? Okay. So what we have is this plus 36.87 degree, which comes up to be 359 by 30 is, I will write 12 approximately, sine theta plus 6.87 degree. We have got this. Now there is the other load, which is the inductive load. ZL is 6 plus J18. 6 plus J18, and now we are not doing for the delta. So it is 18.97. I will approximately write 19 angle tan inverse 3, 71.57. Now for the delta, connected system, what we have is line voltage is phase voltage. So if we have VAB here, what we can get is IAB is VAB by Z. So that is 440 root 2 by 19 sine theta minus 71.57 degree. So 440 root 2 by 19 will give you 32.75 sine theta minus 71.57 degree ampere. Now this current is flowing in the phase. We have to find out the line current. Line current will be, that is what we called here IT. Line current will be 32.75 root 3 sine theta minus 71.57 plus 30 degree. So answer times root 3 gives me 56.72 sine theta minus 31 point, sorry, now these two currents we got here and here, their addition, vector addition, will be the final current. So IA line is 2 thing, that becomes equal to 12 angle 6.87 plus 56.72 angle minus 41.57. I'll use the complex feature of my calculator. Which gives me 65.3 angle minus 33.66 degree. So this is the line current. This is the line current. Now, what is the power for a three-phase system? The power is root 3 VL IL cos phi. So root 3 line voltage they gave 440 volt. 440 times 65.3 times cos root 3 times 440 times 65.3 times cos. Let's give somewhere around 41.42 kilowatt, and power factor is cos 33.66, which is 0.83 lagging. Whenever you are asked to find out power factor, you have to mention lead or lag also. Otherwise, that is not complete. Alright, then already over time today. We'll call it a day. Next day, same time, we will meet and I will see about this phase. Okay, Monday 6 p.m.